Thank you. And I shall try not to cry. So just to remind you briefly, the mission of C5 is concerned with radiological protection of the environment. And again, the aim is to ensure development and application of approaches to environmental protection that are compatible with radiological protection of man, we should say humans, and with those for protection of the environment from other hazards. You've seen this particular graphic where I talked on Tuesday about the parallel pathways where we have for humans the reference male and female, the reference person, and the construct that we've done for protection of the environment is to develop the reference animals and plants. And David Copplestone walked you through the application of the methodology and how you might go about making an assessment using the concept of RAPs. We have 12 RAPs, but there's more to it than that. We have a variety of life stages. As I had again mentioned on Tuesday, we look at the terrestrial environment, the aquatic environment, including marine and freshwater, and the idea with the RAPs is that it would provide a fairly comprehensive but not an overwhelming number of species that can be found on a largely global scale. As I had mentioned before on Tuesday, in doing the dose assessment, we have taken the approach fairly simplistic and analogous in many respects to what was done in ICRP2 back in the 1958-1959 timeframe, where we assume that our organisms were ellipsoids of varying sizes, and it's a fairly straightforward manner to calculate the energy absorption from either external or internal sources. And it's a relatively accurate methodology, but it requires some simplifications. And as I noted before, we have our view of the world where it can be a giraffe, although that's not a RAP, but a deer, an earthworm. They're all sort of compressed into these ellipsoid structures. Now, this kind of approach actually works fairly well in the way that we have done a lot of our sampling and analysis over the years. If you've done any sort of environmental sampling, typically what has happened is our focus has been on protecting humans. We will go out, we will collect a sample, we might strip out the bone, but oftentimes we just throw it in a blender, whiz it up, count it, say in a gamma spec, take that data, measure the activity in it, and then using some sort of dose effects relationship, we would make a prediction, either dose to people, or now we're making an assessment of dose to the organism based on this distribution of the activity throughout the volume of the organism. Again, it's fairly simplistic, but it seems to work reasonably well. But there's an alternative approach, and again, if you look at the evolution of radiation dose calculations for people, they went from the small spheres for organs, moved towards more construct and on into the voxel models. And the nice thing about using this approach for the RAPs is, again, it parallels what has been done for humans. It's very understandable. Our colleagues in the other committees have really ironed out the process. And so it allows you to do fairly accurate representation of anatomical internal structures. There's a process where you can build these now from CT and MRI. And again, it allows you the opportunity to do really detailed analysis of radiation interactions, either from external or internal sources. Okay. So why more refined dosimetry? I mean, if you have just average tissue concentrations, why isn't that good enough? Well, as Jacqueline talked in the previous discussion, we really want to know, we want to unambiguously be able to relate dose to effect. And you can only do that if you really understand what the organ doses are. And so in order to do that, you really need to have an accurate model of the organism. There has been a fair amount of controversy lately. I had a question on Tuesday regarding cataracts in the lens of the eyes of birds either at Chernobyl or around Fukushima. You can't really answer that question unless you know the dose that's being delivered and try and relate that to some effect. Doing this sort of approach can help you in your field measurements and how you collect information. And again, it puts us on parity with human dosimetry approaches. So it's not particularly odd or strange. So the process to create these phantoms is laborious, but that's why I have undergraduate and graduate students at my beck and call. The idea is that you would take an organism, typically post-mortem. We have a veterinary college. They are used to having any number of odd creatures run through their CT scans. So you take an image of it. You then, with the images you've created, you have to identify the structures. You can run some software. There's 3D Doctor, Voxelizer. You have to know what your tissue composition is. You add your radionuclide or your energy of your contaminants into the file. You run a code, MCMP. I'm in a nuclear engineering department. That is a piece of software that's very common to many nuclear engineers. And then what you can generate are absorbed fractions. You then take that and match it with your intensity, your emissions, and you generate dose conversion factors for specific radionuclides. So the process looks like this, where you take an organism. A crab was the first one that we did. You get these images. For each one of the slices, you have to identify the critical structures. You build this voxel model. That becomes input to your MCMP. You generate your absorbed fractions, pair it to what you know about the radionuclides, and you get your dose conversion factors from the process. It is laborious. It takes a lot of time, but it's relatively straightforward. Okay. So the question is this, why should you do it? Is it any good? And I'm going to show very briefly some comparisons of the voxel model to the simplified model for 4 of the wraps for a variety of radionuclides, just to give you a sense. And what I'm doing in this particular comparison is I've taken 1 megabecquerel of activity. I'm looking at 7 different radionuclides. They're shown here, 4 different wraps. And I'm looking at one of 2 possible scenarios. In one case, the radionuclide is partitioned, very highly partitioned into a single organ. So this gives you the source to target sort of arrangement that you may be familiar with in doing human dosimetry. The alternative is to take that same activity and simply distribute it between in the entire mass of the organism and then compare dose rates. Okay. So the extreme partitioning of a radionuclide into a single organ is extreme, but it's not unlikely for many radionuclides. For example, you think of iodine-131. In the human body, a large portion of that radionuclide goes into a very, very small organ. The rest distributes sort of uniformly, but about 30% can go into the thyroid, resulting in a very, very high dose. So I'm going to show you just very briefly some graphics, and they're a little odd, so I'm going to take a minute and explain them. What I've done is I've made a comparison, and I don't want to blind my colleagues with the laser. The red line in the middle represents complete agreement between the voxel model and the simple model. And if it's on the left-hand side, the dose calculation using the simplified model says is a greater dose. On the right-hand side, the dose rate using the voxel model is higher. And I'm looking at a variety of sources, so my activity's in my spleen, and it's irradiating itself, or the lungs, or the liver, or the kidney, and a variety of other organs. So again, this is a fairly standardized approach. So let's look at strontium-90 in a rat. Okay, so we're including yttrium-90 in the process. Again, the red line indicates perfect agreement, which you don't see. What we know about strontium is it's likely highly partitioned into particular tissues, so this is not necessarily an unrealistic explanation. And what this shows is that the simplified model would likely, under these circumstances, underestimate the organ doses. So this is an example where we're comparing a highly partitioned nuclide and the dose that's delivered to a variety of organs versus taking that same activity and just distributing it throughout the organism. And again, strontium-90, largely a beta emitter. Chlorine-36, so we're looking at chlorine-36 in a crab, right? This is a very long-lived, essentially pure beta emitter. Typically, we think it's probably going to be uniformly distributed in tissues. So in this particular simulation, what we see is that the homogeneous model generally predicts higher dose rates. So we would say, all right, this simplistic model for this radionuclide is conservative. You probably, you can use this particular approach. Going on, looking at another organism, this is a sand dab. This was the second phantom that we created. And looking at cobalt-60, so this is a beta-gamma emitter. If you look at data on cobalt, it suggests that it tends to concentrate in the kidneys, so this is another one that might partition. In this particular simulation, it's not exactly clear what's driving the differences. It may be mass issues, maybe position of the source, because this is a flatfish, it's not a big, full football-shaped organism. So this is something we would want to look at to understand why are we seeing significant differences. The Trout Phantom is one of our most recent ones, probably the most detailed one that we have done to date. We're using this actually in conjunction with some folks at ANSTO to look at how radionuclides moving through the gastrointestinal tract may contribute to dose to the GI tract. So looking at cesium-137 in the trout, what we see that cesium-137, again, it's a beta-gamma emitter. It distributes in the soft tissues. And in this simulation, the voxel model is probably not conservative if you see it actively partitioned or highly partitioned into muscle tissue. Cobalt-60 in the trout, again, this is a beta-gamma emitter. And what we see is the voxel model frequently predicts higher doses. So the homogeneous model is probably not conservative. So, okay, what does all this mean? So just to show you, for one of our organisms, the flatfish, we looked at all of the source organ tissue combinations for alpha, beta, and gamma emitters. And so we wound up with 871 source to target values that we were comparing. And looking at this, again, the red line shows you where there's perfect agreement. The red values are beta gamma emitters, the green is pure beta, and the orangey yellow is for alpha emitters. And what this says is that the homogeneous simplified model is conservative primarily for pure beta emitters, less so for others. And for the alpha emitters, it's probably largely just due because of the short range, and you're simply concentrating it into smaller tissues. So if it's distributed throughout the organism, you're sort of averaging or lowering the dose. Rat, similar sort of thing. In this case, 166 target source volumes, and the homogeneous model was conservative mainly for the beta-gamma emitters. On to the crab, again, 176 source target values, conservative mainly for the beta-gamma emitters. And finally, for the trout, we compared 871 source to target values, and the homogeneous model was conservative only for the pure beta emitters, not so for the others. So what does this mean? The simplified models are fairly straightforward to calculate dose. They may not necessarily be appropriately conservative when the radionuclides are highly partitioned into organs, but they also may be too conservative under other circumstances, which might lead you to actually overestimate dose and therefore expect impact where none is likely to occur. The key thing is the organism size and organ size is important. The partitioning is important. Now, we are also doing ongoing work with other of the RAPs. We're building voxel models for the bee and the worm. We have some preliminary absorbed fraction data, but one of the challenges is we don't have good tissue composition data for the bee and the worm. So we're in the process of doing dissections, trying to estimate organ densities, and we'll be doing the comparisons shortly. These are just examples. These were generated using micro-CT that are used within university teaching hospitals for imaging rats, rat brains typically. And the challenge for us, as I said, is finding good data on tissue densities. Elemental composition is really key to understanding radiation interaction. And for example, we didn't realize until just about a month ago that the bees have small inclusions of iron in their fat tissue, which helps them navigate. And that's really kind of interesting. But if you're thinking about radiation interaction and energy deposition, that's going to make a big difference in how dose potentially is delivered. So in conclusion, these two models don't necessarily agree all that well. Now, the examples that I've shown are definitely extreme cases, but really what it says is that we need further exploration between the voxelized and homogeneous models. We need to look at how radionuclides are partitioned into various tissues. We need to do more in-depth calculations of internal and external dose fields. And really what we need to do is make a good determination of when and where these detailed dose calculations are required. So thank you very much.